Okay, hello and welcome to my channel. Today we're gonna be continuing the hydrogen atom, and this time we're gonna take a look at the eigenstates, energy diagram, and get our wave function for the hydrogen atom. Okay, so I believe last time we left off at the recursion relation. Okay, plus L plus 1. Okay, so we finished with this, I believe. Right, so this is our recursion relation. Now let's truncate this guy. Okay, so truncate, that would means 1 over kappa would have to equal to minus 2 k plus L plus 1. So here we can move our 2 over, and we keep most of these. Well, actually, no, we don't need this. I'm sorry. Okay, we can move the 2 down here and keep the rest. And what we have here, k plus L plus 1. K and L here are quantum numbers, our very first quantum numbers. And this is also equal to another quantum number, which is n. These are all quantum numbers, and actually k, people use the capital N for k instead, and that is our radial quantum number. This is so I'll just write radial. This guy is orbital angular momentum. Orbital angular momentum. And this guy is the principal quantum number. And from these names, you can know that like n is the almost the most fundamental and also one of the most important quantum number that we have. Okay, so from here, you can also utilize your 1 over 2 kappa to kind of write your En, your energy eigenvalue again, because remember last time, right somewhere, last time we have kappa square equal to minus En over 2z square E square over L A naught. Okay, so from this we can rearrange and write our energy again as minus z squared E squared over 2a naught times 1 over n squared. Okay, so this is what we're gonna use as our energy eigenvalue. Okay, so now that we have this, let's go and take a look at the eigenstates. Okay, so for eigenstates, we're gonna have a chart, but the first I'm gonna write your quantum numbers and kind of let you know the range of these first. So you see from here, you get that n plus L is equal to n little n minus 1. N plus L is going to equal to n minus 1. And these guys are going to range from 0 to n plus 1, of course. 1, 2 to n plus 1, and minus 1, I mean. So these have to be greater than, greater or equal to 0. Okay, so with these we have a sort of chart. The chart of L and N. With this, divide it into, well, maybe go up to 3. Okay, so if this, you put in your dots and link them together with a diagonal line. Here it's gonna be here, 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 here. Okay, so these are your diagonal lines. So these lines are, well, your principal quantum numbers. So here is n equal 1, n equal 1, n plus l is equal to 0. Okay, so n equal 1, n equal 2, n plus l equals 0, these equal 1, and so on. I'm going to stop at 3. Okay, so this is the first one, n equal 1, this n equal 2, n equal 3. And you can see that this passes through these 2 points. This is this 1 point. And every point that line that is, well, belong to this diagonal line is an energy eigenstate that has the same amount of energy, meaning that they are degenerate. So, well, the way you count this is actually very easy. So first one here is gonna have one eigenstate. The first one gonna have 1. Next one we have 2 dots. This dot is 1 state. This dot is 3 states, because, well, L equal to 1, meaning you also have your M is gonna range from -1 to 1. So this is 3 states plus 1 state equal 4 states for n equal 2. And for n equal 3, we have 1 plus 3 plus this is L equal 2, meaning your M is gonna go from -2 to 2. That is 5 states. So 5 plus 3 plus 1 is 9 states. Okay, so you can kind of see the pattern here already. Is that when you have n number, you're gonna have n square states. So from here you get that with n number, you have n square states. Okay, so that's it for the energy eigenstates. Now we're going to go back and take a look at our wave function. So our wave function here is, we're going to have an extra n to our Lm of the central potential. Okay, so this is going to be split into, well, u of r, but u here is a function of nl. So nl of r, and you're in the central potential, so of course there's going to be the radial part, which is your YLM of theta and phi. Okay, so you're going to have something like that, and you have this. You can put it again in the term that we will use to calculate, which is NLM is going to equal to A R over A naught L, your polynomial. Okay, should I write the polynomial or should I just write the word? Since here it is, well, not really important, because when you calculate, you just put it in your device, your calculator, and it will just do it for you. But I kind of want to write it so that you will know what it meant, what it means, what it gives you. So it is something called the Laguerre polynomial, n minus L minus 1 is 2L plus 1. Next is your the K part. And okay, I believe that's it for the full out form. Well, actually, your polynomial can be expand as well. Oh no, your A can be expand as well. But we're not going to do that. We just have to know the physical property of these components here. Well, for A, it is a normalization constant. So it would, well, ensure that when you calculate the probability density, it would be nice and equal to 1. Next part is our R to the L part. Now this part is of course just going to ensure when R goes to 0, meaning that when it approaches the origin, it's going to vanish. Okay, next is the Laguerre polynomial. And the important part here actually is the n minus L minus 1 part here, which would let us know the well, that would govern the nodal, spherical nodes inside our atom. So this means that, well, with this number, it's gonna let you know how many nodes they are in your atom or in your wave function. Okay, next, the upper portion in the 2L plus 1, that would be the angular momentum part. That would first is that it would, well, ensure the normalization. Then what else does it do? I think it's going to satisfy the constraints of, well, the physical property and the spherical symmetry. Yeah, it does quite a lot, but if you, well, at this level, when you analyze this polynomial, the only thing you care about is the lower lower portion of it, the part that lets you know the spherical nodes. Okay, next one is obvious. This is the exponential decay. So it ensures that if, well, R gets very large, this guy is gonna decay nicely. And last is our spherical harmonics, which I have said is a mathematical concept, and it kind of dictates the shape of this guy as well. So you can see this as a split between behavior and shape. That's one way to see it. Right, so that would be it for the wave function. Now we shall take a look at some examples of these wave function. Okay, so erase this part. So today we're going to take a look at psi 100, psi 200, psi 300, and 210, 211, 310, and 311. Since I think like these are the most important, maybe 4 as well, but you can just know the pattern here. So we have psi NLM, right? So these are gonna be corresponding to size, your shape, and orientation. So that's one thing to remember. So what do I mean by size? So size here meaning that, well, it would obviously increase in size, but it would increase by adding a shell outside of your original cloud. Next is shape. It's going to change the shape and the orientation. It's just going to rotate that. Okay, so let's take a look at our psi 1, 0, 0. Psi 1, 0, 0 is it's gonna be a cloud, and this is your center. Would be something like this. So no shell. Your electron is just here, just the main electron cloud. Next is 2, 0, 0. So remember, n is size, meaning that it increased the size by adding shell. And this is the first shell. Okay, maybe I shouldn't do that. I'll draw like this. So this is the first shell. 210. So first shape changing right here. It's gonna turn into, well, something like this. So like split into two lobes. You can think of it as, well, cut in the middle. Next is 211. 211 is, well, a change in orientation. So this guy is gonna turn to this rotated. Next is our 3, 3, 0, 0. 3, 0, 0 is, well, just like these. It's gonna add another shell. This is our first shell, our second shell. All right, so for 4, 5, 6, you just increase the number of shells that you have. Next is 310. Okay, my pen is struggling quite a bit, but like anyways, now 310, you add one cut in the middle. Well, sort of, but like not really. Okay, maybe this is not the best way to draw it. It's gonna, well, later if you draw like 410, 510, it's gonna resemble sort of the shape of your Wi-Fi symbol here. So for 2, 3 is gonna be like this. Okay, and 311 is you take this shape and you rotate it. I'm trying my best here. Just think of your Wi-Fi symbol. It's like gets like large enough. Also say N10. It's gonna be something like this. Yeah, this is like one way to imagine it. It's like two Wi-Fi symbol, and you just like mirror the upper one to the down. Okay, so that is one way for you to imagine it. Right. So those will be our shapes for the hydrogen atom. Okay, next is energy diagram, our last part. Okay, so maybe I should put it with this. I'm going to erase this part. Energy diagram. It's pretty close to our energy ion state thing. Right. And this is going to be L. This is going to be 1 over n squared, since that would be sort of gap between these. So start with -1, -1/4, -1, 9, minus, okay. L 0, 0, 1, 2. My pen kind of struggling. Yes. Right. So your L gonna be 0, 1, 2, 3. Okay. So first one second one, third one. Okay, there we go. This would be our energy diagram here. So these change with the gap 1 over n squared, right? And this would have the radial quantum number equal to 0. This is 0, this is 0. And then it would increase 1, 2, 1. This is n equal 3, n equal 2, and n equal 1. Right? So we can see for the hydrogen atom, there are a bunch of degeneracy here, since well, here you look at the diagonal line, here you look at the vertical, no, the horizontal line, meaning that this and this would have the same amount of energy. And well, this one is, yeah, this is going to be a 4, it's 9, so 1, 4, 9 is just going to increase like that to n squared, right? So that would be your energy diagram for a hydrogen atom, and that would also be the end for today's video. Goodbye.